Okay, good day everybody. In today's lecture, we want to discuss radioactive decay law. This radioactive decay law is very important to students of different levels. Students in secondary levels, JAMB and all the rest of them, we benefit a lot from here. And students from high institutions, such as students in universities and various fields of studies, such as sciences, medical line, this topic will also be very relevant to the students. Now, states the radioactive decay law. What does it state? Radioactive decay law states that the rate of decay of a radioactive nuclei is proportional to the number of nuclei present in the sample at any given time. So what it entails is dN dt negative is proportional to number of nuclei present in the sample. The negative sign here indicates or implies that the number of nuclei decreases with time. So I'm going to have negative dN dt is equal to, remove the proportionality, you introduce a constant, and that constant is called decay constant. So this negative sign can come over to this place. The whole of this equation is the same thing as this. So I'm going to have dn over n will give me negative this dt. So integrating both sides of this will give me integral of 1 over n dn will give me decay constant integral of dt. Integrating this will give ln, that is natural logarithm of this, which is equal to, integrating this one, dt will give us negative decay constant t plus c. I call this one equation 1. Then taking exponent on both sides of this equation, it's going to give me n is equal to exponential negative decay constant t plus c. Already you know that exponent will cancel this ln, so that's how I got this. And this equation can also be given as this. N is equal to exponential negative decay constant t dot exponential c. I'll call this one equation 2. Then at t equal to 0, I can say n is equal to n naught. What does it entail? It means wherever you see n, you put n naught. Wherever you see t, you substitute 0. So I'm going to have n naught is equal to exponential negative decay constant times 0 dot exponential c. Okay, knowing fully that this one, it gives us exponential 0 dot exponential c. But exponential 0 is 1. Exponential 0 is 1. Exponential 0 is 1. So if I substitute 1 into this place, I'm going to have n naught will give me exponential c, which is the same thing as exponential c equal to n naught. Okay, wherever I see exponential c here, I'm going to substitute n naught into this equation. So if I do that, I will have n is equal to n naught exponential negative decay constant t. At time t, I'm going to have this as this, which is n naught exponential negative decay constant t. So that will give me this equation for radioactivity. And this n of t is called number of nuclei remaining. This is number of original number of nuclei or initial number of nuclei. This is number of nuclei remaining or left or undecayed. Have n of t is equal to n naught exponential negative decay constant t. Then this is general equation for radioactivity. Now, the next one is the half-life. The half-life of a radioactive nuclei is the time taken for atom or unstable nuclei to decay half of its original value. Meaning at t, small letter t equal to t half, n of t is equal to half n naught. So wherever we see t in this equation, we put t half. Wherever we see n of t, we put half n naught. So if I do that, I will have half n naught is equal to n naught exponential negative decay constant t half. Okay? Already you know this, we cancel this. That means 1 over 2 or half is equal to exponential negative decay constant t half. Okay? Taking natural logarithm on both sides. So I'm going to have ln 1 over 2 will give us this one. We can the natural logarithm will cancel this exponential. So you are going to have negative decay constant t half. This one from the normal logarithm, you know that division means minus. So that will give me ln 1 minus ln 2 is equal to negative decay constant t half. But ln 1 is equal to 0. Then negative ln 2 will give me negative decay constant t half. Negative will cancel negative. So t half will give me ln 2 over decay constant, which is natural logarithm. Ln 2 is approximately 0.693. So that will give me 0.693 over decay constant. So this is the equation for the half-life of a radioactive element. This the half-life is ln 2 over decay constant, which is 0.693 over the decay constant. If I make the decay constant the subject of the formula, we have decay constant will give us 0.693 over half-life. Call this equation 6. Substitute this equation into this. So meaning that wherever you see the decay constant here, you put the whole of this. If I do that, I will have this, which is n naught exponential negative, instead of decay constant now, I'm going to have 0.693 over t half of t. This equation can also be modified in this form. N of t will give you n naught exponential negative 0.693 t over t half. T over t half. Okay? So, but t over t half, we call it n. This n is called number of half-lives. We call it number of half-lives. So that will give me, wherever I see t over t half, I will substitute n, which is the number of half-lives. So that will, whenever I see t over t half, I will substitute n. I told you n is the number of half-lives. So if I put that there, I'm going to have n of t will give me n naught exponential 0.693 all into n. Okay? Then, sorry, negative is here, which is this. So remember that exponential negative 0.693 is equal to half. If you press it in your calculator, this is going to give you half, which is 0.5. So wherever you see the whole of this, you put you put half. So n of t will give you half of this and n naught. Call this equation 7. This equation is equation for the radioactivity. This has been modified to be in this form. So I have n of t is equal to half n of n naught. That means the original number of atom, or the original number of nuclei, radioactive nuclei, is equal to number of nuclei decayed plus number of nuclei remaining. I can call this equation 8. The number of nuclei remaining, you carry this one to this place, you are going to have n naught minus n of d. I call this equation 9. Then fraction of the atom decayed. Fraction decayed, fraction decayed. This small letter D here means decay. This F is fraction. Fraction of the radioactive nuclei decayed is giving us number of atom decayed over original number. I call this equation 10. Fraction remaining of the radioactive nuclei remaining will give us number of atom remaining over original number. Call this equation 11. So what I'm going to do now is I'm going to substitute equation 9 into equation 11. Wherever I see number of atom remaining, I'm going to put this one into this place. So if I do that, I will arrive at this. That will give me fraction remaining will give me, instead of this, I'm going to have n naught minus nd over n naught. This can also be expressed as this. You know, this can be expressed as this. Fraction remaining will give us n naught over n naught minus nd over n naught. This will cancel this 1. Then you have fraction remaining is equal to 1 minus number of nuclei decayed over original number of nuclei. I call this equation 12. This is called equation 12. So I'm going to substitute equation 10 into equation 12. So wherever you see nd over n naught, number of nuclei decayed over number of nuclei, original number of nuclei, you put fraction decayed. So that will give me fraction remaining is equal to 1 minus fraction decayed. So in that case, fraction decayed plus fraction remaining will give you 1. This is called equation 13. This equation 13 is a very wonderful equation. Decayed plus fraction remaining is equal to 1. So if you want to make fraction decay the subject of the formula, you're going to have 1 minus fd is equal to 1 minus fraction remaining. Fr is equal to fraction remaining is 1 minus fraction decayed. So you can also have fraction, knowing fully that n of t is equal to n naught exponential negative decay constant t. So when we divide both sides by n naught, you're going to have this over this will give you exponential negative decay constant t. So number of nuclei remaining plus the original number of nuclei will give you fraction remaining. So fraction remaining is number of nuclei remaining over original number of nuclei, which will give you this, which is this. Okay? Now also recall that number of nuclei remaining is equal to half of this n naught. If we divide both sides by n naught, I'm going to have n of t over n naught will give me 1 over 2 of n. Okay? So already you know that number of nuclei remaining over original number of nuclei will give me half raised to power of n. So that will give me fraction remaining is equal to n of t over n naught, which is equal to 1 over 2 of n. This is a very nice equation. This is equation for fraction remaining, and this is equation for fraction decayed. This is fraction decayed. So we are going to conclude here for today. And in the next class, you will get more knowledge about it. We are going to employ these equations I've derived so far to solve some mathematical problems. Please stay tuned. Thank you.